This is section 2.6, Nonlinear Inequalities. The I can statements for this section: I can solve polynomial inequalities and I can solve rational inequalities. If f of x is a polynomial function, then the polynomial inequality has the general form of f of x is less than or equal to 0, less than 0, not equal to 0, greater than 0, or greater than or equal to 0. So we're trying to determine the interval in which our function will be either greater than 0, less than 0, not equal to 0. We're looking for one of those forms. To be able to find this, we're going to use a sign chart. This is a chart that's used to determine on which interval a polynomial function is positive, negative, or not equal to 0. By finding the sign of f of x for just one value in each of the intervals, we can determine on which intervals the function is positive and which intervals the function is negative. So if we take a look at example A, the first thing we want to do is get everything to one side and 0 on the other side. Then we're going to find the zeros of the function first. We want to see what can multiply to get a negative 27, that adds to get a negative 6. This will be a negative 9 and a positive 3. Remember, when you pull them out of the parentheses, you change the sign. So our zeros for this function are going to be at x is equal to 9 and x is equal to negative 3. The next thing we're going to do is we're going to make our sign charts. We're going to make a line, and we're going to input where our zeros are and then find our intervals. So we need to find value that is less than negative 3, a value between negative 3 and 9, and a value that is greater than 9. So let's let our value that's less than negative 3 be negative 4. The value between negative 3 and 9, let's let that be 0. And the value that's greater than 9, let's let x equal 10. So what we're going to do is we're going to go back up to our function. And we're going to input the x values to see what the corresponding y value is. So if we plug in negative 4 first, negative 4 squared is going to give us a positive 16. Negative 6 times negative 4 gives us a positive 24. And we still have our negative 27. And this is going to give us a value of a positive 13. So for the entire interval that is less than negative 3, we have positive values. So we put a plus on our sign chart for anything that is less than negative 3. Now we're going to plug in something from the interval of negative 3 to 9, which in our case we chose 0. So when we plug in the value of 0, we get a negative 27. This is a negative value, so this means all of our y values between negative 3 and positive 9 will be negative. Now we're going to plug in 10. After we plug in the value of x is equal to 10, we will get a y value of a positive 13. So that means everything from 9 and up will be a positive value. But if we go back to our function, we want to know all the values that are greater than 0. So we're looking for the intervals where it's positive. Our function is positive if the values are less than negative 3, and our function is going to be positive if our values is greater than 9. So our solution for part A is that our function is going to be positive from negative infinity to negative 3, or from 9 to positive infinity. Now these are going to be curly brackets because this is just greater than. If this said greater than and equal to, we would have a square bracket at negative 3 and a square bracket at positive 9, because that's when our x's are equal, our y values are equal to 0. Now let's take a look at B. We're going to do the exact same concept. Take everything to the left first, and then we are going to find our x values. Once you have your x values, we're going to put those on our sign chart. Now we need to select values that are in the intervals. So we want a value that is less than negative 7. So let's use an x value of negative 8. We need an x value that's between negative 7 and positive 2. So let's let x equal 0. And we need a value that is greater than 2, so let's use 3. So we're going to take our function, and we're going to substitute in the x values we selected. So let's substitute in negative 8 first. And if we substitute in negative 8, we are going to get a value of positive 10. So we know all the y values will be positive if the x value is less than negative 7. If we plug in 0, we will get a y value of negative 14. So all the values, y values between negative 7 and positive 2 will be negative. And if we plug in the x value of 3, we will also get a positive 10. Again, that means all the values greater, x values greater than 2 will have a y value that is positive. Now for this function, we are looking for all the places where our function is less than 0. It's going to be less than 0 when it is a negative interval. So our solution for this one is it's going to be less than 0 between negative 7 and positive 2. Now if we do know the real zeros, and we remember that we can use end behavior, and we know about multiplicity, then we actually can create our sign chart without actually testing any values. So if we take a look at these examples, let's look at A first. The first thing we have to do is we're going to have to find our zeros. So if you graph that function, you will see that one of our zeros is going to be located at negative 1. So if we go do synthetic division to find our other ones, let's do that first. So our function was 3x cubed minus 4x squared minus 13x minus 6. So we take those coefficients and put them across the top. We think one of our zeros is at negative 1, so we're going to do synthetic division with negative 1. Remember, you bring the first number straight down. Negative 1 times 3 gives us a negative 3. We add straight down, that's going to give us negative 7. Negative 1 times negative 7 gives us a positive 7. If we add down, that's going to give us a negative 6. And negative 1 times negative 6 is a positive 6. When we add straight down, we are going to get 0, so we do know that is a 0 of the function. Again, from the graph, we can pull out another 0, and it appears that 3 is another 0. Remember, if you do synthetic division and you do get 0 at the end, there is no remainder. You can use the quotient of your first one when you're doing the division of your second. 3 times 3 is going to give us 9. 3 times 2 is 6, and that gives us 0. Now we started out, this was at 3x cubed. After doing one division, we're left with 3x squared. After we divide one more time, we'll just be left with 3x. So we're left with 3x plus 2 is equal to 0. So now we can find our last 0. We're going to subtract the 2. Divide both sides by 3. And we have an x value of negative 2/3. So we have x is equal to negative 2/3. X is equal to negative 1. And x is equal to 3. Those are our 3 zeros of our function. So if we go back to our original problem, we can make our sign chart for those values. Those were our zeros of our function, so they're going to be our turning points, or when we change from negative to positive and positive to a negative. Now we can look at the end behavior. If you remember, the degree of your largest exponent will tell you if the function's going to be even or odd, so if they're going to go in different directions or the same direction. Since this is an odd number, we do know the two ends are going to go in opposite directions. Our leading coefficient in this case is a positive 3. So we know our function is going to go down to the left and up to the right. So our function is going to go down to the left. It's going to be negative on the left, but it will be up on the right side, so it'll be positive. On a sign chart, these do alternate, so we'll go negative, positive, negative, positive. So we can find these without actually substituting in any values. If we're looking for the intervals where it's less than or equal to 0, because it has the equal to sign, we actually do have to include where it is crossing, where it is an x value, and that's going to be a square bracket. So everything to the left of negative 1, including negative 1, will be used. This is a square bracket because it does say less than or equal to. And we also will be negative or below the x-axis when we're between negative 2/3 and 3. But again, these are going to be square brackets because it says less than or equal to. On part B, we first need to get everything to the same side of the equation. To make this a little easier to factor, we can divide everything by 2. And then if we factor the equation, we're going to get our zeros for this function are at a positive 2 and a positive 4. Because remember, when you pull them out of the parentheses, you change the signs. Now we're going to look at the end behaviors. So if we go back to this function, our degree is 2, so that's an even degree. This means we know the two ends will go in the same direction. They'll both go up or they'll both go down. Our leading coefficient is a positive 2. Since it is positive, we do know both ends are going to go up, or they will have positive y values, which means it'll be negative between 2 and 4. We are looking for when this function is less than or equal to 0. Again, since it says equal to, these are going to be square brackets. And we're going to be less than 0, or the y values be below the x-axis. between 2 and 4, and it will be equal to 0 at 2 and 4, so they are square brackets. When a polynomial function does not intersect the x-axis, the related inequalities have unusual solutions. So if we try to find the zeros of this function, it's going to be non-real zeros, because this does not ever cross the x-axis. If we were to graph this function, it would look something like this. So if we want to find all the values where our y value is less than 0, since this entire graph is above the x-axis, all of its y values will be above the x-axis or will be positive. So there are no solutions or no real solutions where our y value is less than 0. On part B, it's still the exact same equation, so it's still the same graph. This time we want to know the interval in which it is greater than or equal to 0. Since all of these are greater than 0, they're all above the x-axis. This is for all x values, so this will be from negative infinity to positive infinity. On A and B again, we still have the exact same equation, but this time we can actually factor it. We want to know what multiplies to get 25, that adds to get negative 10. This will be negative 5 and negative 5. So this means our x value will just be 5, so there will only be one number on our sign chart. We can use our end behaviors because this is a positive degree. We know that it's going to be pointing upwards. And because this is, it's an even number, so it's going to be pointed upwards. Since it is a positive leading coefficient, we know it is going to go up. So we do know it's going to be positive y values on either side of x is equal to 5. So if we are looking for values on part A that are greater than 0, it's everything that's less than 5 and everything that's greater than 5. On part B, they want all the values that are less than or equal to 0. Since all of our values are positive, there aren't going to be any that are less than 0, but we do have a value where it is equal to 0. If you only have that one specific number, we're going to write this in sets notation. When you put it inside of these types of brackets, you're talking about a set of numbers. If there's more than one, you can put commas. So we could do like 5, 6, 7, 8 for all the numbers we need. But since our set only contains this one number, it's just the set of numbers that include number 5. Now, a rational inequality is an inequality that contains one or more rational expressions. While a polynomial function can change signs only at the real zeros, a rational function can also change when you have discontinuity or an asymptote. If you notice, we have negative y values here. We have an asymptote, not a 0, and then it jumps and is positive y values right after the asymptote. So we not only have to worry about the zeros for the one function, we need to worry about the zeros in both the numerator and the denominator when we're making our sign chart. So if we look at example A, we are adding two fractions. To be able to add fractions, they first have to have the same denominator. So on the first fraction, we need it to we need to have a least common denominator. So we need to multiply the top and the bottom of our fraction by x plus 1. So we have an x plus 1 on both denominators. Then for the second fraction, we need it to have an x minus 6 in the denominator. Whatever you multiply on the denominator, you have to do the same on top and bottom. So we're going to multiply the second fraction by x minus 6 on top and bottom. We're doing this so we can get a common denominator, so we can add the two fractions together, because we want one large polynomial function, so we can find the zeros of its numerator and its denominator. This will be a rational expression when we're done. You want one polynomial on top, one polynomial on bottom. So on the left side, we're going to have 4x plus 4. We're going to distribute that 4. We're not going to multiply the denominators. We're just going to leave them in the form that they are, so it's easier to identify the zeros here in a minute. On the right side, we're going to distribute that 2. That's going to give us 2x minus 6. Sorry, that's going to be 2x minus 12, because 2 times 6 gives us 12. And our denominator, once again, will be x plus 1 times x minus 6. Now, since we have common denominators, we can add the numerators together. So when we add it together, it's going to become one large function. Now we just need to combine like terms. So when we combine like terms, we're going to end up with 4x plus 2x gives us 6x. And negative 12 plus 4 is going to give us a negative 8. So 6x minus 8 all over x plus 1 times x minus 6 is greater than 0. Now we need to find our zeros of our numerator and our denominator. And we're going to put all of those onto our sign chart. So for our numerator, we have 6x minus 8 is equal to 0. If we take the 8 to the side, it becomes positive. And if we divide, we're going to get a 0 of the numerator of x is equal to 4/3. On the denominator, when you pull them out of the parentheses, you change the signs. So our denominator, we have 0 at x equals negative 1. And we have a 0 at x is equal to 6. Now, the one from the numerator will actually be an x-intercept. It'll be one of the zeros of the function. The ones from the denominators are the asymptotes, the vertical asymptotes for your functions. Those aren't actually zeros, they're asymptotes, but we can change our y values from positive to negative asymptotes, so we have to include them as well. So once we make our sign chart, we're going to pick values that are in each interval. So for this interval, let's use x is negative 2. Between negative 1 and 4/3, let's use 0. Between 4/3 and 6, let's use 2. And greater than 6, let's use 7. Now remember, you're going to take each one of these terms, you're going to plug it into the original function. So we can plug it in down here, because this is still the same function, it's just written in a different form. And if we plug the values in, if you plug in x is equal to negative 2, you're going to get a value of negative 2.5. So this will have negative y values here. If you plug in the value of x is 0, you're going to get a value of positive 4/3. So this is positive in this interval. If we plug in the value of f of 2, or where x value is 2, we're going to get a negative 1/3. And if you plug in a value of 7 for your x, your y value will be a positive 4.2. So they will be positive values here. We are looking for where a function is greater than 0. Our function is greater than 0 when it's between negative 1 and 4/3. It's also greater than 0 if it's larger, if our x value is larger than 6. On the next example, we do not have this as greater than or equal to or less than or equal to 0. So we first have to take that 1 to the other side. Now 1 can be written as 1 over 1. Now for this to be a rational equation, we need to just have one large fraction. So we need to get the same denominators on both sides, so we can combine them and make one large fraction. Since the denominator on the fraction on the left is 4x minus 3, we need the denominator on the right to be 4x minus 3. So we're going to multiply the numerator and denominator by 4x minus 3. One times 4x minus 3 is just 4x minus 3, so our numerator and denominator for this new fraction will just be 4x minus 3. Now since our denominators are the same, we can combine like terms. So if we write this out, we have x plus 6 minus the quantity of 4x minus 3. We do need to make sure this negative gets distributed to both pieces. So now when we combine like terms, x minus 4x gives us a negative 3x. 6 plus 3 gives us 9. So we have negative 3x plus 9 all over 4x minus 3 is greater than 0. We got everything to the left side. Then we simplified it to make it one rational expression. Now we need to find the zeros of the numerator and the zeros of the denominator and put those on our sign chart. Remember, the zeros of the numerator are actually going to be the zeros of the function. The zeros of the denominator will show you where the asymptotes are located. So on the numerator, if we set negative 3x plus 9 equal to 0, we're going to solve for x by subtracting the 9, then dividing by the negative 3, and we will get an x value of 3. For the denominator, if we set 4x minus 3 equal to 0, we take the 3 to the side and then divide by 4, we will get an vertical asymptote at x is equal to 3/4. So when we make our sign chart, we put our asymptotes and our x's on there. We need to pick a value that's less than 3/4. So let's use x equals 0. We need a value between 3/4 and 3, which we can pick as 1. And we need a value that is larger than 3, so we can pick 4. We're going to plug these values back into that function down in the left-hand corner. So if we plug in 0, negative 3 times 0 is 0. 4 times 0 is 0, so we just have 9 over negative 3, which would give us a y value of negative 3. So in this interval, it is negative. If we plug in a 1, negative 3 times 1 is negative 3. Negative 3 plus 9 is 6 as our numerator. 4 times 1 is 4, minus 3 is 1 as our denominator. So 6 over 1 is going to be positive. And as long as each 0 only has a multiplicity of 1, this is going to alternate. So if it went negative, positive, the last one will be negative. We want to know when this function is going to be greater than 0. So it's going to be in that middle interval. So it's when our x values are between 3/4 and 3.